So once you calculated the relative volatility at the two endpoints where x1 goes to 0 or x1 goes to 1 to test for the azeotrope, you discover that where x1 goes to 0, the relative volatility is much higher than 1, greater than 1, and where x1 goes to 1, the relative volatility is less than 1. So definitely an azeotrope does exist. This behavior or this calculation can then be used to predict whether we've got a high pressure or a low pressure azeotrope. So if we want to explain this, let's make a qualitative drawing of each of the two options, the high pressure and the low pressure azeotrope, and consider what would happen with the relative volatility at the two endpoints. When we have a high pressure azeotrope, we can see that y of component 1 will be higher than x of component 1, and therefore this will result in a relative volatility that is higher than 1. At the endpoint, where x1 goes to 1, we can see that mole fraction in the vapor phase is less than that in the liquid phase, which would result in a relative volatility of 1 to 2 less than 1. And this is similar to what we have observed in our calculation. So definitely it seems as if we will have a high pressure azeotrope. Let's just compare what would happen if we have a low pressure azeotrope at the two endpoints. Here the mole fraction in the liquid phase is higher than the mole fraction in the vapor phase, therefore relative volatility less than 1. And on this side, mole fraction in the vapor phase is higher than the mole fraction in the liquid phase, and relative volatility will be higher than 1. And this is the opposite of the behavior that we have in our system, so definitely we have a high pressure azeotrope. So we are asked to calculate for which range of Z values will the system split into a two-phase mixture, and the requirement is that the mole fraction in the liquid phase should be 0.7 in component 1. So since this value of the saturated liquid is given, the temperature is known, this fixes the pressure of our system that we need to investigate. So we can now see what happens for different Z values at this pressure. If this is the value of Z at this pressure, this is the liquid phase composition that will be in equilibrium with that vapor phase. If this is the liquid overall value for Z, no two-phase behavior will be observed since we are in the subcooled liquid region at this point. If I increase my Z value, it will split into two phases, a saturated liquid with this composition and a saturated vapor with that composition. Further increase in Z will lead to the formation of a single-phase superheated vapor at that pressure. It is only when we go past that saturated vapor in equilibrium with that liquid for any Z value within that range, it will in fact split into two phases. Liquid phase composition 0.7, vapor phase composition this unknown value over there. So what are we asked to do? We are asked to calculate this range of compositions, Z low to Z high. And hopefully you realized by now that Z low corresponds to this bubble point Y that is in equilibrium with our given value of X. So once we have calculated the pressure, that fixes that pressure of our system, we can calculate the mole fraction of the vapor phase in equilibrium with a liquid phase with a fraction of 0.7, and that fixes our low value for Z. This, of course, corresponds to our high value for Z, and that is the answer that is required.